So my name, as Stuart said, is Jon Hayes. I've worked for Atkins Realis for 27 years now. So I started when we were called WS Atkins way back in 1998. I was a graduate civil and structured engineer at the time. Moved into PWI, became a PWI CRE and eventually a CEM. And that's where I am today. Since 2020, I've been working on the Crewe BHIL resignaling project as CEM for design, and obviously working for Atkins Realis with Balfour BT, TSO and Network Rail as part of the Central Rail Systems Alliance. So I'll move into the presentation. So today's topic is solving the drainage problem. So I'm going to explain what we did there. So first of all, I thought I'd give you a bit of context about Crewe, if you don't know. Crewe is a railway town. It started by the Grand Junction Railway Company. The first station was built in 1837, and the locomotive works was constructed in 1842, moving from Edge Hill in Liverpool. And in 1846, the London North Western Railway was formed. Additional lines were built, creating the six-way junction that you see on the plan there, which is as it is today. And then the other major development that happened was, which is relevant to this presentation, is the construction of the independent lines, which happened in 1896. Took 5 years, finished in 1901, and that was to take the huge amount of freight that was running through the station away from those passenger lines and take it underneath the North Junction and down parallel, and then joining back up at Basford Junction to the south. That photograph there, you can see what they call the Big Dig happening at the time. That's just where Rail House is today, if you know Crewe. A lot of kind of steam-driven plant and hand excavation, and not a inkling of PPE by the looks of it. Next, so BHIL resignaling. So BHIL stands for Basford Hall and Independent Lines. The project was primarily a resignaling project driven by life expired signalling equipment, so effectively a signalling renewal. But in doing that, you take the opportunity to enhance things by recontrolling everything to Manchester Rock, and unfortunately that meant the abandonment of and closure of 3 signal boxes, which have now gone, physically gone, or in the process of disappearing. They're at Basford Hall Junction to the south, SS North in the middle of the freight lines, and then Salop Goods Junction a little bit further north. So it was primarily a full resignaling, recontrol. That was done by Siemens. CRSA did everything that Siemens didn't do. So we did the track, the OLE and traction bonding, drainage, civils, temporary works, earthing and bonding, environment, topo, and then we had some subcontract designers that came on board to help with elements of the drainage, such as the auger boring, dewatering, and cured in place lining, which I'll tell you about later. So BHIL resignaling was the resignaling of 3 control areas. So on that diagram, apologies to anyone who's colourblind and can't see, but it's the yellow area, the minty green area, and the red area of the 3 signal box control areas. So quite a lot of the track footprint in Crewe was affected, which is why the job has taken so long, basically. Just an example for those of you familiar with signalling scheme plans. This was one of the most complex ones I've seen, and yeah, I tore my hair out on a daily basis looking at that. But it's a complicated scheme. It's a really complicated junction, and that's just what you end up with. So that shows the kind of complexity we're dealing with in terms of the track works, and also trying to drain that track footprint. track interventions. So there were several areas of track interventions which were primarily either adding in or removing trap points, driven by the signalling design. And there's also an area of kind of recovery of certain elements of track that were redundant, taking an opportunity to improve the alignment. New signalling assets, and this is where we come to why the drainage is important. So you've got signal gantries, REBs, lokes on loke stagings. There's an OLE structure there that was to enable the signal gantry to go in. And then we've got new TPWS, more new REBs. There's an axle counter head there, and you got UTXs, cable route, disc boxes, and track circuit leads in those photos. So yeah, it's a heavy presence of signalling infrastructure going in to renew what's there. So we come to the drainage. So why was the drainage scheme required? Well, that photo on the left kind of tells it all, really. The two lines running through here are network rail running lines. The down fast, down slow, independent, track circuited, but when they're underwater like that, the track circuits fail. So network rail, we're getting a lot of downtime and kind of not being able to run trains whilst that was happening. And obviously there's perturbation in the timetable there, and then costs from Fox who want to use those routes. So yeah, not good for network rail, and they wanted to address that and make the new signalling equipment that was going in robust and free from faults. A couple of other photos, so you can see this one on the right, that's a little bit further south towards Salop Junction, completely underwater there. And then a couple of others showing the track underwater at SS North, which is just a bit to the right of that photo. So not great at all, and something that needed to be rectified. Just a bit more detail. So we needed a drainage scheme in relation to a re-signalling scheme because of the track circuited signalling detection, which is a low voltage current runs in one of the rails. And when that doesn't work, then you don't know where trains are within the railway between IRJ sections. There was regular existing track circuit failures due to flooding, and Network Rail wanted to introduce that reliability and resilience. Poor drainage obviously contributes to poor track quality as well, and there were horrendous amounts of twist faults around, and the track was suffering, the sleepers were rotting, etc., etc. And it's not good for trying to maintain a railway and avoid derailments on that complex junction area. Also, at the time, or earlier in the project, this was going to be used as a diversionary route for renewals of Crewe Station area, and possibly still might, I don't know, but that was the plan at the time. So we wanted to have that resilience there as well for running passenger trains through here. So there's lots of new line-side infrastructure, all of which would be susceptible to that water damage because it obviously runs with electricity, which doesn't like water. 4 new REBs, signalling loke cases with the associated 650 volt signalling power system running in those cable routes and UTXs, points operating equipment, TPWS, AWS, and points heating, all of which don't like being underwater. Just a few more pictures of those kind of assets that I'm talking about being susceptible and where the water can impact on them, and you can see that it's just not good. So what we needed to do with the drainage early days was just work out what's going on. Where does it outfall to? Where are the main drain runs? Why is it not functioning at the moment? Where are the problems? So this was the only record drawing that we had to go on. And I think that dates from, that's showing the drainage that went in Victorian times originally. So the main outfall is Gresty Brook Culvert, which is it's a brick arch culvert about 4 or 5 meters deep below the railway running across here. on the next one, you can see the 1877, before the independent lines went in, just the West Coast Main Line had gone in at that point. It was a stream. Technically, it is a river, albeit quite small, but that ran across there like that. And then when the independent lines went in 1896 to 1901, you got a map from 1908 there showing its course has been routed through a culvert under the railway and straightened up. And as a result of that, also I imagine this would have been running in a bit of a valley, if it's anything like this, the same watercourse further west. So the railway would have been filled in, hence the reason the culvert's so deep. But yeah, that's the culvert as it is today, and that's the natural outfall point for all the drainage in the area to run to. That's the current situation. So the culvert runs across here. It's about 450 meters long in total. The most recent extension, I think the end of it used to be here, and it got extended with a new reinforced concrete box culvert structure all the way to here to allow for expansion of the track materials handling site. So a lot of surveys had to go on in probably the first 2 years of the design phase, grip 3-4 stage. So we just had to spend weekend after weekend on site, looking in all the catch pits, utilising jetting and CCTV and dye tracing to try and work out where everything ran to and from. So the first thing you do is obviously look in the culvert and see what pipes are poking in. That's your starting point. So we had 2 pipes here come at that point there, and then there was also a manhole here that we call manhole 4, which was our only access into the culvert really, and there were a couple of pipes poking into there, one from the north, one to the south. So really they were our focus. We had to try and use those existing outfalls as much as we could, mainly because they're there already, and getting a new outfall agreed with the Environment Agency is a lot more problematic and cumbersome than reusing an existing outfall. So this is what we found with the surveys. So predominantly stuff coming in from the north. So we found a chamber here that looks like that. So a standard kind of catch pit, but deep. And then there were a couple of precast concrete ring manholes here, chamber B1 and B2, that looked to have been installed in the late 90s, but there's no record of why, presumably to fix some kind of collapse. Then there's chamber B, which is this one here, which is a deep brick shaft with catch pit rings on top. And then you've got A1, which took some real finding. We were finding it with a CCTV, but couldn't see any evidence of it on the ground, and it was buried under about a metre of fill. So that took a bit of sonding and CAT scanning and surveying to try and find that position. But once we did, it helped massively. And then chamber A, which is immediately adjacent to the culvert, and that's the location of those 2 pipes poking in that we saw on the previous slide. And then you've got a 16-inch pipe coming in from the south there, and a 300mm pipe coming in to manhole 4 from the south, and that's basically it. So all of our drainage design needed to utilise these existing drains, mainly because they're running at depth, underneath all of this railway. I mean, this is an embankment here, so to redo any of this drainage and find the same outfall, you'd have to excavate very deep and disrupt the railway enormously, and we didn't want to do that. So there was once we established this and established the condition, because there were some collapses, the next thing was to try and fix that. So yeah, as you can see, here's some of the blockages. So this is coming into the culvert from the south, and the 16-inch pipe. This is manhole 4, got a concrete blockage that to this day, even though we've now excavated down onto it and put a chamber there, we couldn't really work out why that was there. and then this was between chamber A and A1, so on that main outfall coming from the south. So what we ended up doing with that was lining it with the cured in place liner that was installed by I-Line. So all they needed was access from each end, and from that they could remotely repair this collapse using kind of an inflatable balloon type installations, and then patch repairing, and then putting the liner in afterwards. So clever stuff, and saved the project millions and millions of pounds, because this is 5 meters deep, running diagonally under a railway junction. So the thought of trying to dig down and repair that in situ with standard kind of excavation support, it just wouldn't happen, because you'd need so much time to do it, and the railway can't be closed for that long. So here's our proposed drainage scheme in total, some parts of which haven't happened yet, but you can see it runs for a good, what is it, nearly 2 miles, 1 3/4 miles from the south end to the north, near the tunnels on the north junction. Split into networks depending on which outfall they're going to use. The focus today is talking about network 2, which is the purple one there, which is the biggest of our networks. Bit of a zoom in on network 2. So that starts just south of the A500 overbridge, and then runs all the way up down Independent Cess, and then outfalls into Gresty Brook Culvert here. The blue areas are the areas of flooding that were apparent on those photos early doors, so really need to sort those out. As it turns out, we also have ended up outfalling network 2A into network 2 through the same separator. I'll come to that later, but that was a bit of a optioneering and design refinement, because originally network 2A and network 1 here we're going to outfall into another separator here and use the Manhole 4 outfall, but that wasn't particularly buildable and would have been expensive, so this was the solution. So network 2A also feeds into that and sorts out another area of flooding. So what is the deep drainage problem? So on network 2, it's a long network, 1.26 kilometers from end to end. It's a filter drain, so a perforated pipe in a pea gravel trench, effectively. Exceeded about 3 meters in depth on approach to the outfall, just due to the length and the need for a constant fall. Drainage working by gravity. So we needed an oil separator to comply with EA guidelines, particularly because the section that we're draining is prone to oil contamination from stabled locomotives and locomotives that are stopped at signals and things like that. So even though the area is electrified, there's a predominance of diesel locomotives pulling the trains there. So yeah, that oil separator needed to go in. That was stipulated by the Environment Agency. So that's our fixed endpoint effectively for the drainage network. We also agreed with the Network Rail Pre that drainage greater than 2 meters requires a separate filter pipe above the deeper carrier pipe. So that's called a filter carrier system. So less than 2 meters, you just have a filter drain with a perforated pipe. Below, deeper than 2 meters, you then need a carrier pipe, and also then a shallower filter pipe that drops into that carrier drain at every catch pit. So that is more difficult to construct, and we had that on the approach to the outfall on network 2. Default installation method, and one we'd used on the other shallower networks, was trench cut and cover with trench support temporary works. This was deemed extremely difficult in a constrained 6 foot, which we had here. So, I mean, the down fast, down slow independent 6 foot that we had the drain running in predominantly was tighter than average. It was also very highly curved, that alignment, so very difficult to fit catch pits in, and also to excavate deep trenches and get trench support in, and then get large pipes in as well. Ground conditions were also poor, so heavily saturated clay with bands of sand, running sand in some places, and yeah, just collapsing, very high water table due to the Lord knows how many years of non-drainage activity that's gone on. So the whole area was saturated, and it was just the worst possible conditions for trying to dig a trench and support it and work safely and get a new drain in that was of any kind of decent quality, that, you know, to have a decent design life. Pipe sizes on as you get towards the end, we're getting up to 600 mil or 600 mil ish, which is pretty big, and working space, as I said, is pretty tight. I mean, in places we even, you know, we pulled the sleepers through to give us more space, cut sleeper ends back to make room for catch pits and the like, but still it wasn't feasible where you get too deep near the outfall. 6 foot install we decided would require a track off, which we'd done somewhere else and had some good idea of the cost of that, but that would have, I don't know, added hundreds of thousands of pounds to the job, and also required extra design for the track alignment, and we'd probably ended up putting loads of existing deficiencies in the track right as part of that, and ended up renewing it, because that seems to be what happens, you know, scope creep. You can't just take off what's there and put it back. You have to take the opportunity to renew things, and it's cost that the project couldn't really muster. So that was out of the question. So we had to, there were numerous constraints also in the routing of the drainage due to just the track layout, position of the OLE foundations, and other infrastructure like cable routes and points heating transformers and ground signals and stuff like that. So here's the problem. So you've got the drainage coming in this wide way from the north there, if you can see my cursor. The first obstruction you've got is 4 loke cases, which have to be maintained until after the signalling commissioning, when they're then redundant, but until then they're a risk to the existing system if you damage or disturb them as you go past. So we wanted to avoid those. There's a ground signal in this 6 foot here, and then you've got OLE structures. There's a portal there that's got a switch on it, another portal here that, as it turns out, had a very shallow foundation that would have been, the bottom of the foundation was shallower than the invert of the drain pipe that we'd been putting in next to it, so would have effectively undermined that foundation by going past it, which is not good. So we had to avoid that as well, and we did even look at kind of trying to replace that structure to remove that risk, but the costs again were prohibitive. There's also Siemens' new overtrack crossing gantry here that they put in, which shows how difficult it is to excavate and get UTXs and the like in for cable management. Just easier to go up and over rather than under in this track layout. And then you've got the authorized walking route there that everyone uses to cross over. So all of those constraints led us to do a lot of optioneering to look at different solutions for how we could get that deep drainage through there, and then to the so auger boring was what we went with. So in terms of the cost comparison, you've got probably 1.15 million for doing it with standard excavation techniques and trench support, versus about 800 grand for auger boring as a rough comparison that I think we put in the TQ. So it's a saving, and also it gives you a system that will actually be installed in reasonable time, and will give you a good quality product. So the benefits are that auger boring is trenchless. So the way it works is you have a drive pit, which is a larger pit at one end of a pipe run, and a reception pit at the other, which is smaller, and basically you drive a route through and then leave pipes in at the end of that, and I've got some photographs that show that in action. But you can basically, because it's not cut and cover excavated, you are allowed to cross the track at tighter angles than you would otherwise be allowed with a standard drainage UTX. We still had to derogate, but it was granted because of the depth below the track that we were going and the methodology that was used. The pipe had to be carrier only that's installed, because you can't install perforated pipes at that depth, and they were too deep anyway with our kind of filter carrier rules that we're working to. But that did give us a benefit, actually, because that carrier network, which is the one that needs to have the big pipes and to run deep, that can do what it wants to get to outfall, and then you can have a separate shallow filter drain network that, you know, may only be 1 meter to 1.5 meters running where it needs to be to drain the track in the cess, in the 6 foot, and as long as that eventually outfalls into one of the auger boring chambers, happy days. So yeah, we separated the carrier from the filter system, and it worked to our advantage. So auger boring is laser guided, that they put something in initially that they called a probe, which is accurate and basically runs, it's kind of computer programmed, I suppose, is how to describe it. So that probe runs through first, sets the route, confirms that there are no obstructions, which is something you're obviously very concerned about with these things, and gives you good accuracy and as-built compliance for the drainage, and gives you the fall that you need. And as I said before, Network 2A also came into this and outfalled into the Network 2 separator. So the installation method, yep, large drive and reception pits. These were installed using precast concrete caissons, which were driven, and I've got a photograph of that I can show you, which minimises additional temporary works. So if you wanted to sink a chamber like that and didn't use driven concrete caissons, you would end up with basically a coffer dam, and I'll show you some pictures because we have had to use that technique somewhere. But these ones were perfect because you literally just drive. You have a steel cutting shoe on the bottom of the first manhole ring. You drive that into the ground, and then you excavate the material out, and you just keep going and going and going, adding rings on until you get to depth, and it acts as its own excavation support. So you don't need anything else additional. So it was brilliant from that respect, and definitely a technique I'll look to use on other projects if I ever do anything like this again. Settlement of the tracks in that complex junction area with the diagonal drain runs going across is also key. We manage that with detailed pre and post surveys and monitoring during the auger boring. But I think the predicted settlement was like maybe 5 to 10 mil. And that seemed to work quite well. So here's what we, after all my waffling, here's what we came up with in terms of the route. So I mean, it's not the route that you'd pick if you were going to do a drainage run from scratch, but we tried that and that wasn't feasible. So this is what we've ended up with. So you've got CP42 there, which is a drive pit, another drive pit, CP51 there, and then reception pits on the ends. And that enabled you to create this yellow network of drain runs. So network 2 coming down here and away there, and then network 2A over here on that big long diagonal 68-meter run, tying into CP51, and then through the separator and away. So that avoided all the things that we needed to avoid that would cause us problems. And you can see on the timeline on the right there, I mean, it just went in like a dream, really. Didn't have any obstructions, any problems. The chambers all went into the clay really easily, and the pipe runs all went in without much of a hitch. So yeah, all completed in August 2024. So I'm very happy with that. Here's just a few snippets of the design drawings that our auger boring subcontractor Active Tunneling did for us. So you got plan, section, chamber details, you can see the driven caissons go in way below the design invert level, and then there's a mass concrete plug in the bottom to prevent groundwater ingress, and then we bench on top of that, and also you can see here the kind of settlement window, if you like. The green line shows where the settlement impact will extend beyond the route. So yeah, all of that went in a form B, form 2-3, and Network Rail had to accept that design. So here's the interesting bit, I suppose, the photographs of what we did. So top left here, that's the driven caisson. So you can see it's gone in, and there's just the clay has been trimmed roughly at the bottom. The next step would be receipt of the probe, which I think would be this photo bottom left here. And then after that, you've got the caisson being driven. Oh, sorry, not the caisson, the cans. So the cans are these metal cylinders here with kind of an auger in the middle, and they get pushed through and rotated, I think, and that kind of pulls the spoil back to the drive pit. And then what you do after they've gone through successfully is then pipe jack these concrete pipes in after them, and that pushes the cans out the other end, and leaves you with a nice concrete pipe run. So that's the pipe jacking happening at the bottom there in that photo. And then this one is just a example of one of the, I think that might be one of the rings being lifted in with an RRV or maybe a biscuit. But yeah, a very interesting process, something I'd not dealt with before, but worked really, really well. So here's a diagram of the route to outfall. So there's a Network 1 auger boring run. The solid lines are the carrier drains. The dashed lines are the filter network. So you have the separator, which is in the ballast yard. And the philosophy that we came up with for the separator was to try and use the existing outfall into Gresty Brook Culvert, as I said before. And really the key thing for that was the condition and alignment of this existing pipe here, because it was blocked, as you can see from that photo there, about 2 meters from the culvert. We could never really ascertain where that pipe ran, apart from how it was represented on that old record drawing that I showed you at the beginning. So we had to do the design of the separator itself based on best guess, I suppose, and projection of lines and things, to with the proviso that the first step would be to construct this chamber here, CP54, on top of this collapse, clear that collapse, and then survey further down line, and then we could establish the line and adjust the position of this to suit where that pipe was at this point. And that is exactly what happened. And we weren't far off, to be honest. We were maybe had to move it maybe a meter in this direction to meet this, and the levels worked, and yeah, we're well on the way with that. But I'll come to that in a minute. So this is just a nice aerial photo of the outfall area. So looking south, Network 2 coming in from here, separator planned there, and then chamber A and the culvert is here, running that way. Just actually worth pointing out on this that one major constraint to what we were doing here was this intermediate pressure gas main that ran across the site there at about, I think it was 3 meters deep at this point, getting shallower to about 1.5 meters there. This drainage is running at 4.5 meters, so underneath. So if there was going to be any issue with this pipe at all, any poor condition, if it wasn't lineable and repairable, then we would have had to construct new drainage underneath that gas main, and that would have just escalated the cost enormously and made it a lot more difficult to do. And obviously Cadent Gas would be enormously interested in anything we're doing near that, and it would have just blown the program right out. So it was a massive boost to the project that we were able to reuse that bit of pipe. That's not quite come to fruition yet because we haven't lined it yet, but we've CCTV'd through it and it looks lineable, and there's no enormous collapses in there, just the usual longitudinal cracking along the quarter points of the pipe. Yeah, so that is, avoiding that gas main was a major plus. So in terms of the oil separator, the drainage design dictated that we use a Spell Euroceptor full retention separator. It's a single chamber unit, and it's a big one at 12.4 meters long and 3.65 meter diameter. To install this, we needed a large scale sheet pile cofferdam. Temporary works, they ended up being 17 meters long, 6 meters wide and 7 meters deep, to basically just to get down to the excavation level below the base slab of the separator. And also it was longer than the separator to allow for access scaffold at one end to be able to get in and out of the deep hole. Groundwater was at approximately 4 meters depth, and with us going down to 7 meters, we needed to deal with that water and had to install an active dewatering system. So we put in a network of extraction and recharge wells and a holding tank or header tank, sorry. That was another subcontract design and that had to be done. And the proviso with that was that we needed to have it all done within 6 months of initially recharging. Otherwise, we'd have to apply for a license, and it would have again taken another year to sort out probably. So we were lucky there as well, I think. The separator tank, as standard, can't support traffic loading directly. You need to bridge over it, and it just so happens that the used ballast handling yard location that we're putting the separator in has some of the biggest plant you can imagine, with big loading shovels like the Cat 972 there, and other massive plant dumpers and grabs and whatever. So they're moving around and they're tipping the spoil from trains that have come in from track renewal works. And they're scraping the shovels along the ground and all sorts and running around everywhere. So they're going to be tracking over that separator. So it needed to have a very, very robust cover slab that spanned the full width and length of it, and also had to be flush and chamfered and make sure it didn't get knocked and damaged by the buckets of the machines. So what we ended up doing with that was having a cover slab in the design that spanned over the interceptor and utilised the sheet piles as in the permanent case in the design. So rather than taking them out at the end, the sheet piles stayed in, became part of the design, and I think that made the cover slab design a lot simpler than it otherwise would have been, I think, in terms of what it's spanning onto. So that was a good innovation there, and also I think in retrospect, pulling the sheet piles out could have kind of created more damage than it's worth in terms of the surround to the separator with the concrete. So yeah, a good result. Just a small additional point on the separator. So separators need to be vented to enable, avoid the buildup of gases from the oil and whatever else is in there. And also you need monitoring equipment in there to inform Network Rail that the oil capacity is getting to its limit and it needs emptying. And also there's on this site we have a penstock chamber as well, which is CP51, which is the very large drive pit at the end of the network, where someone can go and manually shut the network down and stop, if there's an oil spill. That's kind of an emergency measure that we've got in place on the system, and that alarm and vent are co-located with that penstock chamber in a little compound in the corner of the site that is separate from the ballast handling yard because people can't wander around the ballast handling yard because of the large plant. But they, yeah, accessible by the network rail maintainer whenever they need. So that's what the separator looks like. There's like a nice diagram of the inside. You can see the water comes in here. There's a silt baffle stopping the silt go any further, and then the oil will sit at the top as it tends to, and then you've got this coalescer, and there's an ACD there, which is a control device, automatic closure device, which shuts down and prevents any more outfall to the culvert once the oil level has reached capacity. And so the idea is that the water comes in, the oil sits at the top, and then the rest of it flows through a series of cleaning measures and ends up in the outfall pipework in the culvert a lot cleaner than it came in. And this holds all the nasties and then needs maintaining regularly by Network Rail, inspection and kind of emptying and the like. That's it in place on site, ready to be lifted in. So it's a beast of a thing. Just some example design snippets again. So there's the civils, GAs, sections, reinforcement, detailing on the cover slab, and then just the temporary works GA underneath showing the dewatering with the recharge wells positions. So here's the initial piece of work that we did, the first bit of big civils. So this is CP54, which is the chamber that we landed on the collapse 2 meters from the culvert. So strangely enough, there was a chamber already there, but it was a very, very small manhole ring and was full of ballast. So presumably repairing some kind of previous collapse. So what we did, we found the existing pipe. You can just see it there going across diagonally, and then we joined new pipe onto it, formed a manhole, and then built that up to ground level, and that's the finished article there. And then from that, we could then investigate the pipe further upstream towards the separator area. This is the oil separator installation. So this is the 17 by 6 by 7 meter deep cofferdam, and some guys in the bottom there. They've at this point they've excavated to depth. They've put moved all the soft spots, put the type 1 in the bottom, put blinding concrete on, and then this is them laying the reinforcement for the actual seating slab that the separator will sit on. So the installation of that seating slab was ultra critical. It needed to be perfectly level, and within ideally a tolerance of 0 if possible, because you've got to install these tanks level and you've got to install them so they tie in with the rest of the drainage system. Otherwise, there's just no point in doing it. So that was a relief when that went in, and it went in at the right level and tied in with everything else. So that's it been lifted in by a big crane, and then once it's in position in the cofferdam, that's the stage 2 concrete that's gone in up to just under invert level of the inlet pipe. It's still like that as we speak, because once they did that, they could then move on to these other bits and bobs. So they formed the apertures through the cofferdam there for the inlet and outlet pipe, and then worked on the 2 chambers each side. So the inlet chamber, which is this one, CP52, which is nearing completion now, and then 53, which is this one on the right here, that's the other end of the existing pipe. So we've managed to sheet pile, find that existing pipe again, and it gives us 2 ends now to work from, to line that and to investigate further, and then that ties into the outfall from the separator. So lessons learned, really, just drainage general. Always look for record drawings and archive information if you can. try and work out what the existing drainage is doing. Try and reuse as much of the drainage as you can, because refurbishment is possible, as long as you found your access points, your manholes, your chambers. But it's important that you do that rather than just saying we're going to put new drainage in everywhere, because we need to try and reuse as much of this drainage as possible, because it does save money. It's an MVP thing to do. Always consider constructability and the cost of temporary works and installation method, because it's critical to defining the permanent solution. We found that with the auger boring and with a few other elements of the drainage on this job. And to be honest, this is probably, drainage isn't often done properly, as in given the consideration that it needs, but it needed to be done on that way on here because of the complexity of the track layout and the scale of the networks. But this is really a flagship project for how to do drainage properly, and also how to bring temporary works into it, and work as a proper D&B organisation with design and construction as one. And that went really, really well. I'm very proud of that. GI is also critical, especially for the temporary works, to understand what the excavation support needs to do, and also to understand the level of the groundwater. Obviously, pollution is a key consideration for drainage. So if you've got any potential oil that could come into the system, then that needs to be dealt with a separator, and always liaise with the Environment Agency and try and find your existing outfalls using your surveys above. Climate change, we allowed for, I think, 1 in 100-year storm event on this job in accordance with current standards. So that should provide some resilience in the future for the drainage network. Hopefully we won't see those photos of it underwater again. And yeah, the drainage is important. Don't ignore it, because it'll come back to bite you. And hopefully we've sorted out the problems at Basford Hall. So thank you very much. That's the end of that.
Right, John, thank you very much. That was a really interesting rundown of all the drainage work you had to do, investigation at BHIL. Clearly, those early pictures that you put up really did emphasise, excuse me, the problems that you were facing, and in fact the age of a lot of the infrastructure which you were dealing with. And if I sort of go to the end, the fact that you put up drainage often ignored. Certainly my experience early in working for track many years ago, but it was the lowest common denominator, i.e. the thing that would be sacrificed first.
Yeah.
But ultimately it's the basis on which everything else is a success. So yeah, absolutely agree with that. So we've not got too long left. We've got 5 or so minutes left. So there were a few questions that have appeared in the chat. So if I can go to them in no particular order, I'll take a couple at the bottom first. One from Carl Baker and one from Mark Taylor, because they are similar. Carl asked, did you experience any settlement against what was predicted? And sorry, it was actually Damien Jones who asked the other question. Did improving drainage in the area result in any ground shrinkage, or is this still being monitored?
So on the settlement, I think there was a little bit of settlement, but nothing to cause any concern in terms of the track, the track performance, or the track top, if you like. I don't think we probably had to do a couple of bits of twist fault rectification, but it wasn't so much the driving of the auger boring that caused that. It was where the chambers were driven in. They were the kind of the most sensitive points. So yeah, the auger boring went really. I think it was just the type of clay, the stiffness of the clay, that really helped. And yeah, there wasn't much settlement at all. No. What was the other question? Sorry. The second one.
And any shrinkage in the ground due to the fact that you've put decent drainage in there now?
Not that I know of, no. Although Network 2 still isn't up and running as yet, so we haven't really seen the benefits yet. Say that those last few pictures that I showed you were literally last week. so it hasn't actually started properly draining the area as it should. Although the network is obviously installed kind of upstream and has been running to outfall through an overpumping system at the minute before the separator is completed. But yeah, we haven't noticed any shrinkage, and I don't know how you would, to be honest. We aren't really monitoring for that. Yeah, it's a difficult one.
Okay, thanks for that,
I'm not
Jon.
sure.
No, is Jim Tinian still on? Jim had a bit of a heartfelt question, it seemed to me, with regard to being interested in how you get the client to commit stuff. Jim, are you on? Perhaps you
Yeah,
can ask
I'm
your
here.
question.
So yeah, as a CRE, I kind of dealt with the fallout of trying to design drainage with limited site investigation, often
Yeah.
no site investigation, because access is such an issue for operational railway. And I wondered how you managed to make the argument to Network Rail that you needed such a full site investigation, because clearly an absolute key to the success of your project here. And you know, if you'd been guessing, you wouldn't have been able to do this. But so often we get asked, just make some assumptions.
Yeah.
We can't give you the access. You know, 11 times we asked for a line block to go and do a walkover on an ECML project not that long ago, and we got nothing. You know, well, we got a chocolate teapot in the end. We got a line block. We got a line block on the line we wanted, but not on the line we needed to get access to it. So you know, it's a real issue, and I just wondered how you'd managed to get clients sign up to that, especially with it being a signalling project, you know, and sort of get across that bridge and join up the dots between disciplines.
I mean, it being a resignaling project with, you know, the big money behind it was probably the main reason why we could do what we were able to do, and also just the sheer scale of the drainage network that I think it was 9 kilometers at one point, so it was kind of, the scale of it made it worth doing. But we had good access as well. You know, we had all Sunday day to be able to work, because it's the freight avoiding lines rather than
right.
Yeah, so that really helped. You know, because I think I found it on other jobs since it's impossible to get a jet vac out in a 4 hours rules of the route possession, isn't it? You need something disruptive to be able to do it. So yeah, that was the beauty of that access, really.
Yeah, it's almost like you need to be planning a 5-year hence project now and getting the information while you've got possessions for whatever's going on now. You know, otherwise it just doesn't work, does it? We know nothing about what's there.
I mean, I don't know if Network Rail records are better on, you know, kind of principal passenger routes rather than Basford Hall was like long forgotten.
Yeah, this was the ECML and we had no idea what was there.
Right.
Yeah.
Okay,
but thanks for that, and well done, because actually getting that together was key to your success, and then the clever use of methods is really interesting as well. Thanks, Jon.
No, thank you.
No, thank you, Jon, and Jim, thanks for the question. Another one from Robert Tate, early one. When we were looking at the collapses in the culvert, Robert was wondering whether, do you sort of expect this as general wear and tear given the age of the infrastructure, or in fact is it the work that we've done in maintenance, etc., traffic going over the top that's caused the issue?
So I think every bit of clay pipe that we've looked at on the job is all failing in a similar way, really. So they generally have like longitudinal cracking at the kind of the crown of the pipe and the quarter points, and then a section of that, you know, and they're 1 meter length bits of pipe as well. A section of that will just drop in, but because of the depth we were at, you know, we were like 5 meters down. I don't think track load was probably too much of a factor. I think it is just literally the age of those pipes. I mean, there must be an element of vibration maybe coming through from the track, but yeah, I think it's just the age. They've been in, you know, over 100 years, and I've never really been maintained. So I think also you got the fact that they were half full of silt. So if they're running full bore, you know, the water is running in the top half of the pipe as well, which doesn't help. So I think just a combination of all those things. But I think track loading probably has caused it to a point, but I think it was probably likely to happen anyway, just because of the age.
Yes, we could see the age from the early information you put up, John. It's yeah, very old stuff. Right, we've gone 1:30. I will just say that this presentation is recorded and will be on the PWI website, because I see that's a question that's been asked. But I'll close there, John, thanking you very much for your presentation. It's really informative, and you can see from the chat there's a number of people thanking you for what you've given today. Very
You're welcome.
informative and interesting. So just thinking about, I've mentioned once, 2 weeks' time, if you'd like to come and listen to decision making in asset management and learnings came from Newnham Viaduct, that's 1st of April. I would also remind you that we have a Route to Change seminar in April at Manchester University, if anybody's interested. So please look on the website, see that if you're able to attend or want to attend. Other than that, I think it's I'll say goodbye from us and thank you very much for attending today. And as I say, information is on the website if anybody would like it, and you can see a replay. So